let's do some more Python. So I made this model of the solar system that shows how it can go flat. So here's one of my, and I have an older video, I'll link to this down below. There's a bunch of balls, they start rotating, and they're gravitationally attracted, and at some point they're going to collide, and I'm not happy with the collision model that I made. So I want to rebuild my model for collision, but I did show that it comes into a flat solar system. But the problem is, like, if you don't have collisions, it just oscillates. It gets flat, but it oscillates like this. Okay, does that make sense? Okay, so here we are. This is what I did before. So when I have these two balls, mass balls overlapping, then I can find the vector position from one to the other. And if they're overlapping, I can calculate this force pushing them apart, and that's force of one pushing on two. That's ball two, and then the other one pushes back. They have to be equal and opposite forces. And then I'm just going to use like a spring force, right? So this is just a spring force where we have some spring constant. That's the vector position from one to the other, and this is twice the radius of the distance. So if it's less than that, then it gets pushed them apart, and that's what I had. Here's the code for what that would look like. Let me go over part of the code, and I am going to live code. There was a request for live coding. Live coding will be in this video at the end. So this is just, the idea is to break it into tiny intervals of time, calculate the forces, update the momentum. That's what I'm going to do. So right here I just have two balls. I'm just going to do two balls. I'm not doing a solar system, two balls. So this is the vector R, is the vector position from one ball to the other. And then I set the force equal to 0 each time. And there's no gravity here. Okay. I set the force equal to 0 so that if they're overlapping, then I calculate the force. If they're not overlapping, that force gets set back to 0, and I don't have to worry about it. So they only push each other apart. So then if they are overlapping, I just calculate that force. This is exactly the same as that equation. You do need this norm R here. That gives you a unit vector, because this is a scalar, that's a scalar, but you need the force to be a vector. It's not going to work. And then the force in the other one's just equal and opposite to that. Update the momentum, update the momentum, update the position, update position, and this is what it looks like. Two balls, and they just collide. Okay, so, and momentum is conserved. Momentum has to be conserved for the system since I have an internal force, right? Or if you want to think of F1 on 2 and F2 on 1, they're equal and opposite, so they don't really change the total momentum. So here's momentum of one of the balls, here's the other one, and then the red line is the total constant. Okay, but I need to add a gravitational interaction. It's just the same thing, right? So I just need to calculate these attractive forces that I can add in there, whether they're colliding or not. It doesn't really matter. And this is the gravitational model. So the gravitational force of object 1 exerted on object 2 is this equation right here, negative g, mass 1, mass 2, over the distance between them squared. And then you need that unit vector, don't forget, or you don't get a vector. That's super important. So if I do the same thing and I add in this gravitational force, then I get, and I'm just using some balls. I made up G. I had G as like what, 0.01 or something, just so I can make it work without having to deal with time intervals and stuff like that. I just want to get it to work. We can always get it to the better units later. So here's my two balls colliding with gravity. I turned gravity a little bit higher, and that's kind of cool, right? And so they bounce apart, but then they get attracted to each other because there's a gravitational force. And we see here that, again, momentum is conserved. So yay, right? That's what we want. We want these balls to collide. We want momentum to be conserved. We want them to be attracted to each other. But I want them to stick together, right? I don't want to just have balls bouncing all over for the solar system. I want them to group together and make planets and stuff. That would be cool. So I need another model. So here's the model that I used before, and I call this the stick and calculate momentum. So I have two masses coming towards each other. They have, this is momentum P11 is the momentum of ball 1 before the collision. P21 is momentum of ball 2 before, so that 1 is before. That's ball 1, that's ball 2. And what I want to do is to have them collide and then have the same final velocity, so they're just moved, so they're like stuck together. Does that make sense? And I want momentum to be conserved, so I can just say momentum's conserved. So if I make the momentum conserved, I calculate the momentum before the collision, P12 plus P22. Oh wait, that's after. P11 plus P21 is before, and just make it equal to the ones after, and then I can calculate the velocity of each one, make them equal to the same, and so that's the velocity. P2 is the total momentum divided by the total mass, gives me the velocity of this whole thing, and then I set them equal to the same velocity, and that's what I get. And this is the code for that. So what I did was to make these functions to say, do they collide? And then if they collide, set the momentum. So I calculate the total momentum. I also push them apart, right? So I put them at the separation distance between them, because if you don't, they just kind of slowly creep in on each other, and I didn't want that. That's what this RT and B2 and B1 is. I just set them so that I move them apart, right? And then after that, if they're apart, they won't collide until gravity pulls them again. Set the velocity and then set their momentums. And this is what it looks like. So they just, boom, they collide and they stick together. That's what I want. And they have the same velocity. And momentum is conserved, again, because I made it conserved. Here's where they're attracting towards each other and speeding up. This is just the x component of momentum, right? Because the y component, I can't plot the total momentum. But, I can't plot the vector momentum. So this red line is constant. That's exactly what we want. But there's a problem. Do you know what the problem is? What's the problem? The problem is angular momentum, right? So these collide, and angular momentum is not conserved. That's not what should happen, right? They should rotate or something. And I want to look at angular momentum in my solar system. So you can calculate the angular momentum as r cross p, where r is the position and p is the momentum. And it's with respect to some point, right? You can pick any point you want. So if I pick a point and I calculate the angular momentum, and I'll do that in the code later, this is what I get. It's not conserved, right? This is the total angular momentum before, and then it drops down. And I'm not sure why it's not constant afterwards. But it's not. Anyway, that's not what I want. I want angular momentum to be conserved. So we need a new model for ball colliding. Here we go. I'm going to have a spring push them apart, but once they overlap, I'm going to say there's always a spring connecting them, right? So I have gravity pulling them together, and then once they collide, they're eternally stuck with a spring. So I need that R vector, that same thing as I had before, and it's the same thing, but now I'm just going to not turn it off. That's the only difference. It's just going to not turn off. And here's what I get. And it looks a lot like it did before with gravity, but it's pulled back together a little bit better, right? It's kind of what I wanted. And momentum is conserved. You get these nice, cool graphs, but it is conserved. We're not surprised about that because it's a internal force. And angular momentum is conserved, right? Because the torque on the system is zero. There's a torque. If you think of the two balls as a system, then they have angular momentum. But that R cross P doesn't change because of what's it called? A directional force, a central force. It's called a central force. Okay, so angular momentum is conserved, so that's good, but it's not what I want, right? Because I don't want my planets bouncing around. I want them to be stationary. Okay, so let's add a drag force to our ball. So let's let them collide. We have gravity, we have the spring force connecting them, and then I'm going to have a drag force. So imagine this ball is moving. They're connected, but this ball is moving that way with momentum. That one's moving that way with momentum. And then I have these two drag forces that are in the opposite direction of their momentums. And I can just say some constant times momentum. We don't have to use quadratic drag. It doesn't matter. Any kind of drag will make them, behave, calm down. That's what I want. Calm down balls. This is what that looks like. You notice that they are slowing down, right? Their collision towards each other, but they also slowed down their horizontal motion. They also slowed down their rotational motion. So it doesn't work. Here is the momentum equation. You can see that momentum starts off with some negative momentum, but slows down. They stop. That's not what I want. Obviously, angular momentum doesn't work either. They stop rotating. It's not going to work. Okay, so here's what I'm going to code. Let's make a new thing. I want to have a drag force that conserves momentum and angular momentum. So these are the velocities of two balls before they collide, or while they're colliding, while they're interacting with each other, and they're separated just so you can see it. The first thing I want to do is to calculate the relative velocity. This cyan vector shows the velocity of this ball relative to that one. Okay, it's their relative velocity to each other. That's important. This is their relative position. And those are pretty easy to calculate, right? V2 minus V1 is relative velocity. R2 minus R1 is the relative position. I want the velocity relative to each other along this direction, the component of this velocity in the direction of R, right? I only want to damp this motion towards or away from each other, not rotational motion. So I can calculate that. This vector, I'll call it VR. It's the R component of vector. I'm going to take the relative velocity. I'm going to take the dot product of this and this unit vector, and that will give me the component in the direction of that. Now, I need it back as a vector, so then I can multiply by the unit vector r hat. And then the drag force will be that constant times the velocity. Now, one of the things I'm going to have to do is to make sure once I calculate that drag force, I'm going to have the same drag force on these two. If they have equal and opposite drag forces, then momentum will be conserved. And if they're radial forces, then angular momentum will be conserved. Okay, let's go ahead and do this. Where's my, oh, that's why. I was moving the wrong mouse. Okay, here is, I started the code. I hope you will forgive me, but I didn't want to just do all this silly stuff. I'm going to go over this. Let me run it. There's nothing, oops, that's not what I want. I'm going to run this right here. So I have just two balls. I didn't do the time thing, but it does work. I have the radius of the balls, the mass, the spring constant, the initial velocity. There's my gravitational force constant. And then I make the two balls, B1, B2. I put them places. It doesn't really matter. I give them a mass. I give them some initial momentum. I put that one at 0. We can change that. That's fine. I give them an initial force. I have a drag coefficient. And then I have my time interval and so forth. So let's go ahead and model the motion. Let's just make a move, and then we'll add in the force. We'll just add in the forces as we go along. So let's do that. Let's do this while t is less than 1, right? Because I have a short time interval, and I don't want it to go too fast. I'm not going to run it in real time. I'm going to run it at 200 calculations per second. Let's just update the momentum. Okay. That's all I'm going to do. So b1.p equals b1.p plus b1.f times dt. I have a b1.f. That's the net force on mass 1. b2.p, b2.p. Can you see that okay? I got to keep my eye on this little monitor over here, or I won't be able to see what you can and cannot see. b2.p plus b2.f times dt. Okay, that's your standard update momentum. Now I can update the position, b1.pos, b1.pos plus b1.p times dt divided by b1.m, b2.pos, b2.pos plus b2.p times dt divided by b2.m. And then the one I always forget, update time. T equals t equals t plus dt. And for some reason, this looks a little, that's good. My window's bigger than my, okay, that's good. Let's run it. And yes, I'm using trinket.io, GlowScript, and I'll give you a link to the code. Don't worry about that. So that one wasn't moving, another one moves, nothing really great. and wonderful. That's what we'd expect. Now let's add the gravitational force. They should be gravitationally interacting with each other. So I'm just going to calculate that up here. B1.F equals, oh no, I'm going to calculate R. R is going to be equal to B2.POS minus B1.POS, right? So the vector from 1 to 2. And then B1.F is going to be equal to G times B1.M, B2.M times norm R divided by mag R squared. And so this is the force on 1, right? So if I have the vector going from 1 to 2, that's the same direction as my force. So I don't need to put a negative sign there. I need to put the negative sign for B2.F. It's going to be the same thing but negative. There. Now let's run that. Slowly adding in the forces. Okay, so they're pulling. You can see they're attracted to each other. It's kind of cool. Okay. But I want to now add the spring force. I'm going to do this with this following. I'm going to say this. Contact equals false. And so if they come in contact, I'm going to keep on adding that spring force. But if I'm not in contact, then I'm not going to add the spring force. Does that make sense? Okay. So the first thing I'm going to do, calculate the forces. Now I need to see if I need to add to that force. So if contact, let's see, let's do this. If R, mag R, is less than 2 times R, then contact equals true. They're in contact. Yeah. And now, if contact is true, I know this seems a little weird, so I can say if contact, because it's a Boolean variable. You can say if contact is equal to true, or you can say if contact. If contact, then I want to calculate the force. B1.F equals B1.F plus K times mag R minus 2 times R times norm R. Now, I looked at my code, right? Because you will very easily get the minus sign wrong here for this spring constant. But the important point is this right here. I'm going to calculate the spring force, and then I'm going to add it to that net force already, which is this gravitational force. And that's important because if you don't do that, you would just delete the gravitational force. I want the gravitational force and the spring force, so I have them both in there. And then B2.F is B2.F. It's just going to be the same thing, but minus this. And these two are equal and opposite, and they're equal and opposite, so it should all work. If contact is true. I think that's right. I think it'll work. It's a little bit different than my previous code, but let's just go with it. Did they bounce? I don't think they bounced. I don't think they're bouncing. Okay, this is what I did before. I said contact is false. I did this. I'm not sure if I need that. I did it like this. If they're less and contact is false, then contact is true. And then I said if contact, I said it equals true, but let's just put it back like that. Let's see if that works. Because they don't look springy. That's better. Okay, now it's working. Okay, let's go ahead and do our conservation momentum and conservation of angular momentum plots. So to make a graph, I'm going to say G1. I'll call it G1 graph. I'm not going to give it. I should give it title. Title equals momentum. Let's do quick. X title equals px. I won't put the units on there. Y title equals time, and then width equals 500, Let's do 400. 400 height equals 200. And then I'm going to copy that whole thing. And then I'm going to make another one. I'm going to call it G2. And this is going to be, let's just call this L. I guess I'll put angular. And this will be LZ. Yeah. Now, if you want two graphs, you want to plot two, I want to plot three functions for each graph. If you put your curves in the correct order, it will work. You can also designate where it goes, but I'm just going to call this FP1 G curve. Color equals color dot blue. FP2, this is for momentum. G curve, color equals color dot green. And then FP total, G curve, color equals, I'm not going to put labels on them, color dot red. We can figure that out on our own. And then I'm going to make the same thing under here, but I'm going to call these L's. L1, L2, L total. Now down here I can make my plots. So let's go ahead and plot all that stuff. I'm going to first calculate L. I think I can, this is called. L1 is b1.pos cross b1.pos b1.p. L2 is cross b2.pos b2.p. And then I can plot them. So fp1 dot plot t, and then the x component of p1 is b1 dot p dot x. fp2 dot plot t b2 dot p dot x, and then the total fp total dot plot t b1 dot p dot x plus b2 dot p dot x. Got it. Now I'm going to plot the angular momentum. fl1 dot plot t l1 dot z, and fl2 dot plot t l2 dot z, and then the total fl total dot plot t l1 dot z plus l2 dot z. If that works, I'm pretty impressed because I put a lot of stuff in there, and if it all works, it's just like, hey. Okay, there's the thing. Okay, there's momentum and angular momentum. Conserved. Okay, that's nice. Now I want to add my radial drag force. That's the part that I really want, right? The radial drag force. I got everything in there. So let's just say the following. If contact is true, I have my R, but I need to calculate the relative velocity. So VREL is going to be b2.p divided by b2.m. That's the velocity minus the velocity of 1. b1.p divided by b1.m. So that's my that's v2 minus v1. That's what that is. Now I need VR, the radial velocity. It's going to be equal to the dot product of VREL and R, norm R. But that's not a vector, so I need to multiply it by norm R. That's the same equation I had, right? So there's nothing magic there. And let's call this FR for the radial drag. It's just going to be C times VR. And so this one, for B1, I'm going to say plus C FR, and this one I'm going to say minus FR. That should do it. I didn't save it in a long time, did I? Save. And run. I'm going to look at it first. So it's still rotating and it's still moving, right? So that's good. But the only way we're going to really know is if we check the angular momentum and the linear momentum. So here's my linear momentum. What do you think about that? That looks pretty good. Solid, straight, red line. And then the angular momentum, boom. So I have done it, right? I have made the two balls collide. They stick together. Momentum's conserved. Angular momentum's conserved too. And now I can use this in my model of the solar system with a bunch of balls. Not with two, but a bunch of balls. Of course, I'm going to make that in another video. But but that's a better collision between two balls. And so remember, colliding two balls is easy. Colliding two balls and making them stick together, that's not easy. If you want a little homework, you can check, is kinetic energy conserved? It should not be, right? We obviously have to lose kinetic energy because they're sticking together. And there you go. Okay. Links will be down below later. How do I stop this? There it is.